Hello everyone, Dr. Ziya here. This video tutorial is about vibration analysis and time domain representation of vibration signal. So in time domain representation, so I'll plot response of free damped vibration using MATLAB, and then in the second part I'm going to find logarithmic decrement and damping ratio from the signal. So response of free damped vibration using MATLAB, and I'm going to plot signal as 2D plot in MATLAB. So here is MATLAB, and I have this signal cantilever beam with mass attached at it, and this problem is like as here vibration of a cantilever beam with mass attached. So that is a beam cantilever beam and mass attached, and it is a very common problem in theory. So experimental data for is measured using a sensor, and it gave that time and displacement, time in second and displacement. So here I have that data. So first I need to import that data. So, so I'm going to import that text file as a table, and here is function I am using. It is a read table. So it is a function read table, create table from the file. So T, it, this is a table is equal to read table file name, and then you need to add extension of that. So it might be text file or CSV file. So usually data from any device or accelerometer, so that is usually available in text file, CSV file, or sometimes it is Excel file. And like as here are some examples of that read table. So now this data read table, and it says that column headers of file are modified. So this data here is time underscore s underscore and displacement underscore millimeter underscore, that parentheses are they are being converted to underscore, and then now from that data I'm going to take first column I'm taking it as uh, time, and then the second one displacement. So now I have created two tables, one for time and the other one from like as that is matrix I got. Now representation is very simple. Is very simple. So I am going to use figure, and then I'm going to use plot. And plot command is here, create 2D line plot, and it is very much simple. Like you have to plot and then X and Y, and then like as sometimes you need to add line color. So like as plot XY, and that is dash line, then it's red, R is for red, and this O is for circles, as you can see here. And the other one is like plot XY, and then it is just dots there. And similarly, you can use that XY and then only circles. So what I used here, so I plot time and displacement. So it is a figure one. So like as here you can see, so that is a figure one, and there is no grid on it. And then I'll use the command grid on. So now here is a grid on that figure, you can see, and then I can give it title, I can give X label, and I can give it Y label. So here, and that is time domain response of this cantilever beam. So here you can see, like first a periodic load is being applied till somewhere half second, and then So that periodic force is being removed, like as usually to excite vibration, and then it start vibrating. And because of air damping, the amplitude of vibration keep on decreasing. And the total time for record this signal is 6 seconds. So that is the time domain representation of this signal. In theory, like as and this is a book, Mechanical Vibration, that is a Mechanical Vibration 6th edition. And when we study theory, vibration in theory, so signals are very smooth. Signals are very smooth, or even for free damped vibration, you can see signal that is very smooth. But experimental signals, they are not that much smooth. Like if I want to see here, so you can see the peak is not being measured here, and again peak is not being measured here. The peak is not being measured, again peak is not being measured, and even here. So this is not a pure sinusoidal wave. So in this case, when we have signal like that, so we need to smooth that signal. So next is smooth signal. And to smooth signal, there are so many options. First, I'm going for smooth signal using moving average. So in MATLAB, so there is a function called smooth data. The smooth data function, it smooth the data using different methods, like as here, smooth data. A is a matrix, A is a vector or matrix, and then here is a method, that which method you need to apply, then what is the window size you need to apply. So uh, very conventional one is a moving average. Very conventional one to smooth data, like if you will go for smooth data and just a signal. So just a signal, so it will use default function, which is moving average. And then there are so many other methods, like as here. So smoothing method, especially one of the following method is the moving average over a window of A. So like as window of A, so it takes like uh, 2 points and then take 2 points average or 3 points moving average, or you define it, and then moving median, Gaussian, and then finally Savinsky Gaulle filter. So, like depending upon vibration data, so most suitable according to my knowledge is a moving average, the basic one, and then Savinsky Gaulle filter. So that is also a good one. So now, if otherwise, so smooth data, you can use that smooth data with any of the function. So now here in MATLAB, I'll have that. So now to smooth signal, I use that displacement as D here, and that is a displacement as D here, and then I'm going to replot that one. So to see, so that is now I have figure 2, and then I'm going to use here smooth data. Here you can see smooth data, and I name it as DS smooth moving average 1. The smooth data D is the signal, and that is a method. And then I'm putting comma here, and then I'm going to put the window size. Window size mean like if it is a signal, so window size mean like, so to find average, moving average of this point, at this point, it takes its previous value 1 and its one forward value. So in this case, it takes three values and then take them average. If I'm saying it like moving average using 5 points, So then for this point, it take two forward point and two backward point. So then it take its average. So like in this case, the window size is, let's say, I am setting it as 9. So this moving average, like 3 mean that one point at which you are finding the moving average, one forward and one backward. Like when we are using it as 9, so it means that 4 points are backward and 4 point forward. So now, and so like this one, so I have it now here. Let's see. So let me first clear that one, and then here you are. So now here is the black line is the original signal, and then this is with smooth data. So like that way. Now you can use that another option which is moving average. So in MATLAB instead of smooth, so that one moving mean. So that moving mean is another one. So you use that moving mean A and then K. So K is like K point mean value, and this is another one. So like as A moving A of 3 points. So 3 point mean that it take first 3 point and find its moving average. Then it takes next 3 point and then take that moving average, and then it take third one. So this is one. This is a very conventional way which you use to which you study in the books. Like, but like if we here we can use another one. Like uh, we can take that. So here you can see. So if you are going to window length, if you are going to put that as 3, so for that particular point, at this point, it take one way forward, one way backward, and then it take its average as 3. Or sometime we could use the brackets, and in the brackets it's 2 and 1. So for that point 3, it take two forward values and two backward values, and then it like here it is two backward values and one forward value. So now using that mean, what I have did, like signal and two backward values, two forward value, and then I have plotted it on it. So now on the same figure, like I have plotted that one. So here you can see, and then I am going to put the legend. Legend are original data, and then the first one is using smooth data and then moving average. So I am going to plot. Here is the figure. Now you can see like smooth data with 9, a window of 9, and then the other one is for the 5. So like here in this case, so you can see the signal is slightly smooth, but in some cases that peak is being removed. And then here you'll have that because the signal is very noise, and then if we are using that moving average with the window size of 9, so it has smoothed it too much. But here with 2 point forward, 2 point backward, so it haven't smoothed that much. In this way you can smooth the data. So this is using moving average. So smoothing data, so you can use that smooth data signal. And the next one is smooth data using Savinsky Gaulle filtering, and in that you can use that S Gaulle filled data order and then frame length. It's smooth data function, smooth noisy signal using Savinsky Gaulle filtering. And how is that? Now I will go there. So I can use here smooth data with the method as that S Gaulle, because here in the MATLAB help, here in the smooth data, like the method. So in the method, there are several methods. So I am using that Ascole Swirsky-Golay filter, which moves according to a quadratic polynomial that is fitted over a length of window A. So this method can be more effective than other method when data varies rapidly, because I can see that it is a bit problem with the data uh, at the lower end. So here that is the one you can use that smooth data filter. Oh, sorry, smooth data syntax, or otherwise you can use that here is the Swirsky Golay filtering and then y x order and then frame length. So what it will do in that frame length or in that window, so it try to fit that by using a polynomial of order n, like as here. So like as third order and then frame length is 11. So it takes that like 11 points and then it try to fit a three order polynomial on it. So here, so the smooth data using Swirsky, Swirsky-Golay filtering, and in that case, I have again plotted original data and then here smooth with default values and then regular fit third order with 11 window, and then I'm going to plot here. So now that is a figure 3 here, and you can see here in this figure 3 like that is the original signal in black color, and then with the selected polynomial like third order polynomial, so it follows the pattern of the signal, but that autofit using default values, so it gives a better signal, smoothing signal. So in the, like as here you can see again like selected polynomial is try to smooth the filter, but like autofit command, so it smooth the signal, but in like better way. So there are so many other methods in the MATLAB help available to smooth the data. So there are so many other methods available. So this is all about time domain representation. So like this is the original time versus displacement signal, and then this signal you can see here. So it is not a smooth. So we are expecting in theory a very fine sinusoidal wave, but it's not. So then we need to smooth it using different approaches. So I have just discussed here two approaches, so you can learn those further. The next part of the video from time domain representation or from time domain plot to calculate logarithmic decrement and damping ratio from signal. So like as you have in the theory, so usually for damped vibration, the signal looks like that way, but I have just demonstrated that it's not that one that much clear. So this figure is from Mechanical Vibration by S.S. Rao, 6th edition. So that is damped vibration, and for that vibration, so from this signal, we can find out its period of oscillation, damped period of oscillation, and then we can calculate from here damping ratio. First, we need to calculate its logarithmic decrement, which is delta is equal to ln x1 over x2. But like as here, I have just showed you that the signal is not that smooth. So for that case, I'm going to use this formula. Lambda is equal to 1 over m ln x1 over xm plus 1. So if we are using multiple, if we are using multiple wave, multiple waves or multiple cycles. So and then from once we have delta, so we can find damping ratio. So from this book, I have taken that expression delta and then zeta. So now, first I'll select a signal, then I'll find its delta and then damping ratio. So that is the original signal. That is the original signal, and then I am taking its part from 1 second to 4 seconds. So I am going to select the data from uh, 1 second to 4 seconds. And for that one, I have here. Here you are. Again, I'm going to select the data, import the data, and I'm going to import data. So that data has been imported. And now from the time I am trying to find, I am trying to find uh, first the index, like when the time is nearly equal to 1.0, and j when the time is nearly equal to 4. So then I'll get that time, which is the time from 1 second to 4 seconds. So here I have, so you can see this one. So that is the same signal. Now I have plotted it from 1 to 4. So now when we have this type of signal, so then we can select values manually from there. Like we can select manually, but like as uh, we can do it using using script, but when we have like this type of stuff, so it will become for difficult for script to detect, like as here. So signal is not very much clear. So what we can do here, we can either find out the values manually, like I can pick the values, or otherwise I'll write a script and that script will automatically calculate it. So now the first one, I'm going to select those points manually, and I'm going to tell you that how is that possible. So let's say I'm going to select this point, this peak. So on the figure, I'll like this one, data tip. So here you'll have that data. And then correspond on here, on the below one, I'm going to select that data. And with the control, here I'll select that. And then with control, I'll pressing control so I can get the second point. So like as on the peaks, and if I consider this one as 0, so that is a 20-second peak there. Or I have selected peaks for like for 21, 22 cycles. And this one from the peak, like this is the crest, and that is from the trough. So now this data, x is correspond to time and y correspond to displacement. So I can use one pair here from the peaks from positive side, and then one pair from negative side. So from here I am going to find delta as delta 1, and from here I'll find delta as delta 2. So now here I have m, because in the formula I have m, then x1, or I'm using here as x0, so it will become xm. So that is a formula. So m is 22 in this case. X1 or x0 will be x0 will be 8.434, x22 will be 4.475, and for the other pair, x will be like the displacement that will be minus 8.297 and minus 4.346. And then here horizontal axis is time. Horizontal axis is time. So that x values pair is for time. So here now I have find out x0, that is a displacement, xm, that is a displacement at the selected 20 seconds, that is a t0, that is tm, and then I use that delta is equal to 1 over m into ln x0 over xm, and t is equal to tm minus t0 over m. And similarly, for lower points, I got the values. So if I'm going to run it, so then I can find out here the values as I have delta. Here it is 0.0291. From that delta, I found out zeta, which is 0.0046. And then the period of oscillation, which is t, 0.0145 second. So this is, I can do manual picking of the data. But the other one, what I can do is I smooth that filter. So once I'll smooth that filter, and then I'll do that automatically. So here, what I did, I smooth the data using moving average of like as window 9. So here, if I plot it, and then what is going on here? So like one of them, here the blue one is the original data. Blue one is original data, and then the other one is smooth using a uh, using window length of I have smoothed it. Okay, and then I find out sampling frequency. I find out sampling frequency because here I am using a built-in MATLAB function. Built-in MATLAB function here. So built-in MATLAB function find peaks. So find peaks of that data which is being smooth. So in the MATLAB help, I can go here is find peaks. So PKS is find peaks of the data, and there are so many other options. And then here, so you can simply use that data, and then if it is find peaks, so if you can, if you are going to input first and second output, so it will give you peaks and then location. So peaks like as here in this one. So what is the value of peak and what is the location on x-axis? So either you can use that with the data, peaks and location, with the data find peak only, or you can find out sampling frequency. Sampling frequency is like in 1 second how many values are there. So I use here a function. So like as sampling frequency, it is find time nearest equal to 1. So when I calculated that sampling frequency here, so it comes as 501. So it takes the first point when the time is 0. So I subtracted it as 1. So the sampling frequency for this sample is now uh, now it is 500. So then I find out peaks and locations using sampling frequency on smooth data. I am using here displacement 2. So displacement 2 is the smooth data using moving average of window 9. And then plot location. Now I am going to, because what will happen in this case, uh, so plot location and then peaks and then like K is a black color, O is thingy circle. So I am going to plot that on the same one, same figure. So now you can see So that are the peaks. Okay, so sometime here are the peaks. You can see, so these are the peaks with the moving average of 9. So sometime if I take that moving average of, let's say, sorry, window 5, so then what is going on here? So then it is going to pick so many peaks. Like the local peaks it is going to pick. So then you need to smooth that data so that it only pick positive peaks. Okay, so with the 5 you can see it is picking some peaks, and with the 7 again I'm going to plot it and we'll see again it is going to pick that 2 peaks, and here 2 peaks here, 2 peaks here. So then you need to smooth that data. So I have used here 9, so you can change it for your convenience. So and then here I got that one, and now from here I can see here like M. So I'm taking the first one and the last one. So the peaks total. So total locations here are 29. So I selected M as length of the location 29. X0 is the first peak here. That is the first peak. And XM is the last peak. And similarly, T0, it is T0 at the locations 1, and TM is the location end, and then T underscore A will become TM minus TO over M, and then delta and then zeta. So in this way, I can find the values. So I don't have to pick from the I don't have to pick from the figure. So now when I use that smooth data, so it is 0.0048, and then with the manual points, it comes as 0.0046. And the time initially from here, I calculated it is 0.1045, and then with that script, it comes as 0.1010. So this is your choice that how you are going to, you can calculate, you can use the manual calculation, or then you can automatic calculation using the script. But in the script, you need to observe that if you are getting right values. Okay, so that is all about finding uh, logarithmic logarithmic decrement and damping ratio. I hope you like this video. Thank you very much for watching. So please subscribe my channel for other videos on vibration analysis.